So we're going to take a look today at what happens if some of our data is paired. So instead of having the differences of two means, it's really just the differences of one mean. So we'll first of all start off with what paired data is. Then we'll look at confidence interval and hypothesis testing for paired data. So basically, you have a situation where you get your data paired. One value is paired to another, and you're really looking at the differences in those values. So it could be a situation where it's a before and after treatment when you're looking at one person and looking at the change before and after. It could be where you're dealing with identical twins and you're randomly assigning one twin to get a treatment and one twin not to get that treatment. Or it could be a situation where you're trying to take into account the social-economic status of somebody, the natural intelligence of somebody, and all these other characteristics, and you're trying to match two people that are very similar in all those characteristics, and then you're looking at the differences between them. So consider this situation here. So what is this situation? It is paired data because you have 50 men who on their upper lips once had tears and then once without. In other words, it was the same man that got both treatments, and you're comparing the results of both. So you're getting one difference, which is your data point, from each person. Now, we could have done this if we and had separate data where we would have been doing the differences of two means, and that would be if we had two totally different groups. One group of men getting real tears, one group of men getting fake tears. But by pairing them together, we eliminate some of those possible confounding factors and our variability becomes less. So that's what we like about paired data whenever we can. But we had paired data because each man got both the real and the fake. We took measurements of each, and we subtracted those two measurements to get our data point that we were going to be using. So decide if this is paired data or if this is two separate samples. This is paired data because we have a before and after situation. You have one man sitting down, getting the before temperature, the after temperature, and you're looking at the differences in that for each man. Looking at this one here, this is also paired data because you have identical twins, and identical twins are great for paired data because of all their similar characteristics. This is actually two separate samples. The reason we have one group of men here, and then we have another group of men. So we have two totally different groups of men. It's not one man seeing a picture with a red background and one man seeing a picture with a white background and measuring the difference. It's two totally different groups of men. So it's two totally separate samples, which would be a differences in two means for this situation. What about this one here? Well, this one here is also paired data because we're taking into account when we're matching these students from one class to the other class, we're taking into account IQ, family income, math ability, reading ability, and all the demographic characteristics. So yes, they're different students, but they're matched up very similarly, so it's paired data. So if we have two totally separate groups, it's the differences in two means that we've done before. But if it's match pairs or one group, then it also goes back to something that we did before with the differences, or not the difference, but just the test of the mean and confidence interval of a mean, of a single mean. And once again, we like to have paired data because it takes into account a lot of the variability that can occur from one subject to another subject. And this goes back and mentions the whole idea of that variability from one group to another group or one person to another group. Match pair takes into account a lot of that, so it can decrease your standard deviation of your responses. So when you're dealing with match pair, it's really a single mean. So your standard deviation of that single mean is what we've looked at before, the standard deviation of the sample over the square root of that sample size. Your test statistic is the mean of all those differences for that paired data, your t star and your standard error. Your t statistic is the differences. I said test statistic here, sorry. That's your confidence interval. Your test statistic is over here. It's differences in those means, x bar, over that standard error. It'll be a t-distribution if it is larger than 30, with the degrees of freedom being one smaller than your sample size. So let's see if these tiers make a difference. So we have our standard deviation, we have the average, and we want to know, do female tiers lower the male testosterone levels? And if so, how much? Well, how do we do this first one? Well, that is our test. How do we do the second one? That's our confidence interval. So here's our key data. We'll go ahead and we'll state our hypotheses, which is we're assuming there is no difference, so it's equal to 0, but we're thinking based on what we've been looking at, there is a difference, that it's going to be lower. We check our conditions, which have to be a sample size greater than 30, which we have. We look at our standard error, which remember is the standard deviation of our sample, the 44 or 46.5, over our sample size of the square root of 50, and we get 6.58. We calculate our statistic, so we take the difference, our x bar, over our standard error, we divide, we get negative 3.3. Then we calculate our p-value. We remember our degrees of freedom is always one smaller than your sample size. It's lower tail because it's less than. And we get a p-value of 0.0009. So how do we get that? We would go to stat. Sorry about this. You would hit left tail, which is off the screen. You'd make sure you looked at your t-distribution, put in your degrees of freedom being 49. Then you go down here, click on this box, and type in the test statistic of negative 3.3. And you get your p-value, which is just off the screen here, which is what we had on the other screen. So what does that mean? It means we have very strong evidence because our p-value is less than our normal alpha or significance level. So we have very strong evidence that the exposure to female tears decreases the average testosterone in men. But the question is, how much does it decrease it by? And that's where the confidence interval comes into play. So we check our conditions. We have to be larger than 30. We knew that from the last slide when we did our test. We find T star, go to stat key, hit T distribution, hit 49 for your degrees of freedom, hit the two tail, It'll pull up your 95% confidence interval, and the two numbers in the very bottom, left and right, really we only need the one on the right, gives us 2.01. We calculate the standard error. Well, we did that on the last screen, so we just write that down. So we calculate our confidence interval. We take our mean, 21.7 negative, plus or minus our t star that we had from step 2, times our standard error we had from step 3. We take our t star times our standard error, we multiply those together, we get 13.23. Then we go ahead and we add and subtract that to our mean. So when we subtract this, which is our margin of error, from our mean, we get negative 34.93. When we add this, which is our margin of error, to our mean, we get negative 8.47. So what does that mean in the context of this question? We're 95% confident that the exposure to female tears decreases the testosterone level in men between 8.47 and 34.93 picograms per milliliter on average.